So let's pick up where we left off last time. So we were talking about cylindrical, oops, let me spotlight myself. We were talking about cylindrical and spherical coordinates. So first of all, I was like, okay, let's remind ourselves of polar coordinates in R2, right? So instead of an xy point, you have an r theta point. And we have some formulas that allow you to translate between them, like x equals r cosine theta, y equals r sine theta, and then we know that x squared plus y squared equals r squared. Okay, using all these things, you could work backwards or to translate between polar coordinates and rectangular coordinates in the plane. So what we want is to extend this to work in 3 dimensions, not just in 2 dimensions. Okay, so I have my axes here. Let me put my pen. Okay, right, so you can see the x-axis right here. You can see the y-axis right here. You can see the z-axis right here. Okay. So you have your 3 dimensions. And whenever we draw a point, like our point P is right here. There's our point P. Hopefully you can see it. It's like that red dot. If you're using rectangular coordinates, you can think of, so if your point P has coordinates x0, y0, z0, you could think of first starting in the xy plane, right? So you start at your origin and you walk along the x-axis to x0 over here. And then you would move out from x0 some y amount parallel to the y-axis, and you would end up at this green point right here on the xy plane. Okay, so this green point right here is on the xy plane. Okay, and then to get to your 3rd dimension, you just like sprout up from that point on the xy plane. You move up in the z direction. Okay, so you have your point x, y, z. Or x0, y0, z0. Okay, so how do cylindrical coordinates work? Well, they're an extension of polar coordinates. So because this green dot right here is on the xy plane, you can give it, what's the word? Polar coordinates, there we go. You can give it polar coordinates because it's on the xy plane. All right, and what would the polar coordinates be? Well, it would be r comma theta. All right, so r would be the distance from that green point to the origin. So you can see that I've made a green line right here. So that's your distance r. And then that radius, it has some theta that it's rotated from the x-axis, which is why in green I have right here this little line showing rotation with the theta, right? So r and theta work exactly like how polar coordinates work. So you get a point on the xy plane, and then what do? You sprout up by some z amount, which is why polar coordinates are in 3 dimensions. The r and the theta are in the xy plane. They're just like polar coordinates, and then the z value works just like the z value for rectangular coordinates. You go up by that amount. So I'm going to pause and see if there are questions so far about how this works in the drawing. Need some reactions, people. Does this idea make sense so far? Sometimes I worry I just speak into the void. Like that sad Doge meme. I've showed you the Sheem meme, right? Where it's like the big beefy Doge, and it's like, I demand the respect of my students, and then there's like the Sheem. And he's all like, oh man, is anyone listening to me? I don't know, man. Like Morty. Okay, cool. So let's do an example where we convert from cylindrical to rectangular coordinates. Example: convert the cylindrical coordinates 4 comma 2 pi over 3 comma negative 2 to rectangular coordinates. Okay, so luckily this works basically exactly like what you would do with polar coordinates, because they basically are polar coordinates. The first two numbers, your r and your theta, those basically are polar coordinates. So those equations we had from a chapter ago, x equals r cosine theta, and y equals r sine theta, still apply here. But let's sort of draw this just so you can get an idea of how polar coordinates work. So I'm going to draw an x-axis. I'm going to draw a y-axis. And let's do the z-axis in red. Okay, so that first number 4 means that your point is some distance of 4 away from the origin. So here's my origin, and I can draw like a little circle. So this circle here has a radius of 4, right? All we know is that our point is some distance of 4 away from the origin. So hopefully that makes sense why I'm drawing that circle here. Now the second number, the theta, tells you the amount of rotation away from the x-axis. Right, so you would start here at the x-axis and you would rotate away in the by the amount 2 pi over 3. 2 pi over 3 in radians is, well, pi over 3 is 60 degrees. 60 times 2 is 120. Did I do that right? 2 pi over 3 is 120 degrees. Daphne, pi over 3 is 60 degrees, right? Yeah, so 120 degrees. So I didn't really draw this correctly. Well, actually, I mean, yeah, good enough. So really where I end up is like somewhere like right here. Right, because the amount that we rotate by is 120 degrees. So right here, I end up with a point on the xy plane. I moved 4 away from the origin and I rotated 120 degrees. Okay, and then this negative 2, that's the z value. That's how I'm going to move off of the xy plane. So I'm going to move down by 2 units to right here, and that's going to give me the point 4, comma 2 pi over 3, comma negative 2. But that's it expressed in polar coordinates. So I want to express that in rectangular coordinates. So we make the change. So I plug in the values. What's my x value going to be? Well, I plug in my r value of 4. I plug in my theta of 2 pi over 3. Okay, I have to do the same thing for y. I get y equals 4 sine of 2 pi over 3. Okay, so let's work on this. So we're dealing with the sine of 120 degrees. Oof. Okay, what's the reference angle of 120 degrees? It's 60 degrees, right? So the sine of 120 is basically the sine of 60. So let's draw a 30, 60, 90 triangle. Because I never remember these values off the top of my head. So there's 60, there's 30, you have a 1, you have a root 3, and a 2. So I want the sine of 60, which is, yeah, root 3 over 2. Okay, then what about the cosine of 60? The cosine of 60 is half. Except for, okay, yeah, so then you have to take care of it. It will be negative, right? So this part right here is going to be negative half. So 4 times negative half is negative 2. And then 4 times root 3 over 2 is going to be 4 root 3 over 2, which is 2 root 3. So what are the x, y, z coordinates of this point? -2, comma, 2 root 3, comma, -2. And that actually makes sense from how I've drawn this. Because if you look at that point on the xy plane, you can see that it has a negative x value, right? Because it ends up in this quadrant over here. Right? It has a negative x value and a positive y value, and the z values are the same, right? So you can see that you move -2 in the x direction, you move positive 2 root 3 in the y direction, and then you move down -2 in the z direction. Okay, so just want to ask, does it make sense how I was able to take my 4 comma 2 pi over 3 comma -2 and draw the point? And are there any questions about getting the x and y values? So I'm just going to give you a moment to look at this and see if you have questions. I'm going to quickly go pour coffee while you look at this. Would you like some coffee? It's over here. We got cafe. Coffee. Okay, looks like people are good. Okay, so let's talk a little bit about surfaces in cylindrical coordinates. Okay, so these equations are going to look a little unfamiliar. So you have to remember that, okay, why is that not letting me write? Okay, your variables are r, theta, and z. So your equations might look something like r equals 2, or theta equals, let's just make up a number here, pi over 4. Or, I don't know, z equals 3. So if I say an equation like that, like what sort of shape do you get if you were to graph it? That's what we want to talk about. So let's start with theta equals pi over 4. Okay, so I'm going to draw my x-axis, draw my y-axis, draw my z-axis. Okay, so remember r is your distance from the origin. So we're not specifying a distance from the origin. So you can get any point, or sorry, a point of any distance from the origin. So a point of any distance to the origin, as long as that point forms an angle of theta equals pi over 4 with the x-axis. So I look at my x-axis, and then what I'm going to do is I'm going to rotate theta equals pi over 4. And you get a lot of different points. So here, let's like these points, they're on the xy plane. Does it make sense that any point along this line is rotated the angle pi over 4 from the x-axis, and they have different r values, right? So all of these points right here, they have different r values, but they all form an angle of pi over 4 with the, what's it called? X-axis. Okay? And then also you have one more variable, you have the z variable, so we can, any point that's any distance from the x-axis, and it can also be have any z value. So you can like extend this up and you get a plane like this. Okay, so if you look at this, it's like it's a plane, it's a sheet of paper. You take that line on the xy plane and we extended it up. Any point on that plane forms an angle of pi over 4 with the x-axis and has any given z value. So the equation theta equals pi over 4 has as its graph this plane. Hopefully I've sort of drawn it so you can see it well. Okay, let's look at another one of these. Let's look at z equals 3. Okay, so what do you get if you just graph z equals 3? Well, what you get is all the points which have a z value of 3. So what that looks like is the xy plane shifted up by 3. So that's like what I'm trying to draw right here. So hopefully you can see it in red, right? This thing, what it is you took the xy plane and we shifted it up by 3. So if you were to graph z equals 3, you get this flat piece of paper like this, which is the xy plane moved up by 3. So if you have equations of like theta equals a number or z equals a number, you get some sort of plane. Now, specifying an r value gives something different. So let me draw another plane here, or another set of coordinates. You have your x, y axis, and then you have your z axis. What will an equation like r equals, what did I have, 2 give you? This is telling you that you want all the points which are a distance of 2 away from the origin. What sort of shape will that give you? Like if you think of, oh what? Not quite. It does contain a circle, so you get like more than just a circle. So on the xy plane, here are all of the points that are a distance of 2 away from the origin. But you have an extra dimension. Like for instance, I'm going to go up the z-axis by 2. Yeah, not a cylinder. Okay, it wouldn't be a cylinder because if it was a cylinder, you would be able to go up from that circle. But if you take a point on the cylinder, the distance wouldn't be 2. It's not an ellipse. It's not an oval. So, it's a sphere, right? You want all of the points that are a distance of 2 away from the origin. That's a sphere in 3 dimensions. There's a bunch of different points that are a distance of 2 away from the origin. So r equals some number gives you a sphere. Theta equals a number or z equals a number gives you a plane. Alright, you can think of it. A sphere is just a ball. That's all the points which are equidistant from some other given point. There's a radius of 2 that's like being swung around in a bunch of different dimensions. Let's do another one. So what about more complicated graphs? What about if you wanted something like a r squared plus z squared equals 9? So let's draw our axes. X-axis, y-axis, z-axis. Okay, so what you usually want to do to figure these out is, so you'll take your equation and notice we have 2 variables now. So what it's useful to do is usually to set some sort of value equal to something. So for instance, let's set z equal to 0. So if you set z equal to 0, where do you know you're going to be graphing the leftover? So if z equals 0, you get the equation r squared equals 9. Where would I graph r squared equals 9? Because z equals 0. Yeah, exactly. So z equals 0 is the xy plane. Now r squared equals 9. Oof. So what does that look like? So r squared equals 9 means you get two solutions. R equals plus or minus 3. So does that make sense? So r equals plus or minus 3. Wait. If z equals 0, it's on the xy axis. I'm sorry, xy plane. Yeah, I'm messing something up. 1 second. Oh, yeah. So if r equals 3, does it make sense that I get this circle of radius 3 on the xy plane? There we go. I don't know, I just lost my train of thought. I was like, what the hell am I doing? Okay, so there's that circle of radius 3. Why do I only get one circle, even though r equals 3 and r equals negative 3? That's a good question. So this has a radius of 3. Let's actually draw it. Why am I only going to get one circle if I graph r equals positive 3 and r equals negative 3? Let's draw our circle in here. Speak to me, people. Why only the one circle? Okay, I guess that doesn't really work really well. Well, we're not going to get a cylinder for this. Let's plug in another one. So if you set z equal to 1, where's the graph going to take place? Yeah, the distance is always positive. Alan's right. So even though we have r equals 3 and r equals negative 3, you can't. The radius of negative 3 makes no sense. So if you set z equals 1, you're going to get r squared plus 1 equals 9. But where am I going to graph this thing? Which is going to be r squared equals 8. So where will that graph take place? Where am I going to graph r squared equals 8? Which is the same as r equals plus or minus root 8, which is plus or minus 2 root 2. So where will I graph this? Right, so, but where exactly? Right, so it's the xy plane moved up by 1. So you move up 1 to right here, and then you move out 2 root 2. What's that as a decimal? So what is the 2 root 2 approximately? So square root of 2 times 2 is 2.8. So if you go up by 1, you're going to graph a circle with a radius 2.8. So you're going to get this circle which goes like this. It's a little smaller than the other circle. Oops. I'm trying to graph it, but I'm not doing a very good job. Let's go up to z equals 2. So that's just higher up. So now you're going to get r squared plus 2 squared is 4 equals 9. So you're going to get r squared equals 5. So you get r equals plus or minus root 5. What is root 5 approximately? Square root of 5 is 2.2. So you get a smaller circle. Okay, and then what happens if you go to like z equals 3? So if z equals 3, you get r squared plus 3 squared is 9 equals 9. So you get r equals 0, which means at 3 you get this point. So I'm getting these like circles that are getting smaller as I go up. And actually what you end up getting is a sphere. It's a little weird. Because what's happening is you're going higher up, the circles are shrinking. And if you look at a sphere from the side, that's like what's happening. Like, do you see how there's like these circles as you go up on the sphere? Right? If you look at a sphere, there's like circles that get smaller and smaller as you reach the top. That's like what we had here. Okay, so like usually what you want to do is like visualize these by plugging in different values. These are called contour curves. When you do this, when you set like z equals 1 and you get this circle. When you set z equals 2 and you get this circle. So it's a good idea to just sort of plot these contour curves to sort of give you an idea of what the shape looks like. Okay. Okay. Let's now, oh yeah, sure, you want to scroll up a little? Like, is that enough? Okay, cool. I'll pause for a minute. Okay, cool. So let's talk now about spherical coordinates. Okay, spherical coordinates are also in 3 dimensions. Okay, and let me show you what the variables for them are. So you have 3 coordinates. You've got the Greek letter rho, the Greek letter theta, and the Greek letter phi. Oops, let's draw that better. Okay. And I'm going to explain to you how these work. And we'll do that by drawing an xy axis. Or sorry, not the xy axis, the xyz axes. And showing you how you interpret these. Okay, so let's choose some point. So we'll move some amount x naught in the x-axis. We'll move some amount y naught in the y-axis. You get a point on the xy plane. And then we'll go up some amount on the z-axis to right here. So there's our point P with rectangular coordinates x naught, y naught, z naught. Okay. So, this is sort of like cylindrical coordinates and polar coordinates. We're going to measure the distance from the origin to our point. That's what rho is. So rho is the distance from the origin to a point. So it's basically like what we were calling r before. But now we use the word rho. We do this so that you know that you're talking about spherical coordinates and not cylindrical coordinates. Does that make sense to everyone? We have a different variable, so you don't have to like look at it and you're like, you don't want to like see an R and then be like, wait, am I doing cylindrical or am I doing spherical? Right, so we have a different variable for it. Okay. Now, let's look at the XY plane. You can project. Do you see this little white line? If you were to shine a light pointing down, does it make sense that that little dashed blue line that I made on the XY plane would be the shadow of the white line? Right? So you shouldn't be that surprised. Theta is going to be the angle that shadow forms with the x-axis. So this is all like cylindrical coordinates. All right, so you start on your x-axis. Theta tells you how much you rotate in the xy plane to right there. So let's write this down. Theta works exactly like theta from cylindrical and polar coordinates. So theta is a measure of an angle on the xy plane. Okay, now the weird thing here is that we're going to have another angle. My other angle, phi, so phi is the angle formed by the z-axis and the line segment from the origin to the point. So the way spherical coordinates work are, you start from the x-axis and you rotate some angle. You start from the z-axis and you rotate some angle. And then once you have rho, the length of that line segment, you're going to be able to figure out where your point is. It's a little weird. And the equations, oh, you can't see the writing. Oh my god. There we go. So phi is the angle formed by the z-axis and that line segment, which goes from the origin to the point. Can you see it now? Okay, cool. And there are some annoying equations to translate between spherical coordinates and rectangular coordinates. So let's say you want to know the x value. Like you start off with spherical coordinates and you want the x value. Your x value is going to be rho sine of phi times the cosine of theta. Oh yeah, sure, let's go back up. Are we copying the beautiful drawing? Probably. There's a lot there. Yeah. Okay, I'll wait a moment. Just drink coffee. Okay, so there are some horrible equations to translate between these variables. If you start off with spherical coordinates, how do you get the x value? It's going to be rho times the sine of phi times the cosine of theta. And luckily there's some symmetry to how this works. So for the y value, you're also going to have rho, but now you're going to have the sine of phi times the sine of theta. So do you recognize this from polar coordinates? You see how for the x value it's cosine theta, for the y value it's sine theta. The annoying thing here is that you always have sine phi that remains unchanged. And then to find z, you want rho times the cosine of phi. So these two remain the same. And then finally it becomes cosine of phi for the z coordinate. No theta involved. And this would actually make sense. There's no theta for z because, remember, theta is something that only operates in the xy plane. Right? So it wouldn't be appropriate to use theta to calculate the z value. Right? Because the z value is like independent. It's not just in the xy plane. Does that sort of make sense? Like you might be wondering, like, how am I going to remember this? Like, the way I remember it is that the x and the y values, they're in the xy plane, basically, so they're going to involve theta. But when you calculate the z value, that has nothing to do with the xy plane. So it only involves the phi, which is the rotation from the z-axis. Okay. Now, hopefully you remember from polar coordinates, how r squared equals x squared plus y squared. There's a similar thing for spherical coordinates, but now you have rho squared equals x squared plus y squared plus z squared, because rho is the equivalent of r for spherical coordinates. Likewise, you might remember that the tangent of theta equals, what is it, like y over x? That's still true here. The new thing is finding what your phi is. So phi is equal to the cosine inverse of, this is horrible, z divided by the square root of x squared plus y squared plus z squared. Okay, so we're going to do an example. We'll use these to like change coordinates. I'll give you a moment to write it down. So in our example, let's plot the point with spherical coordinates 8 comma pi over 3 comma pi over 6, and let's also convert. Okay, so we have this point in spherical coordinates, 8 comma pi over 3 comma pi over 6. Let's plot that and then convert them to rectangular and cylindrical coordinates. Okay, so drawing these is always fun. Got your x-axis, got your y-axis, got your z-axis. Okay, so remember the way your coordinates work is that first you're given a rho, then you're given a theta, and then you're given a phi. Okay, so the length of your line segment is 8. So wherever you are, you're 8 away from the origin. So you can sort of imagine that you're starting by thinking of there's a sphere and the radius of the sphere is 8. So here's like, let's put on the the x axis. There's a radius here of 8. Now, theta tells you how much you're going to rotate that radius of 8. I'm going to rotate that radius pi over 3, which is 60 degrees. So I'm going to rotate, oops, I cannot draw today. I'm going to rotate this 60 degrees. So I get to this point right here on the xy plane. Right, and I've rotated by theta equals pi over 3. Okay. Now you do the same thing on the z-axis. You start right here with this thing of radius 8. And then now what do? You're going to rotate pi over 6 away from the z-axis towards my green line 30 degrees. So I'm going to rotate in this direction, phi equals pi over 6, which is 30 degrees. So my point, actually let's redraw this because this doesn't look very good. They're not like lining up. So let me redraw this. There we go. It's going to look like this. Okay, so that has a radius of 8, and we're rotating it. Phi equals pi over 6. This is my point right here. So notice that there's a relationship between these two things. I start with a radius of 8 on the x-axis, and I rotated it pi over 3 radians. I got that green line. I started with a radius of 8 on the z-axis, and I rotated it pi over 6 away from the z-axis, and I got the white line. Now you have to remember that those two things, they're related to each other on a triangle, and the green line is the shadow of the white line, so they have to be lined up properly, which is why I get this triangle here. Does everyone see how I get a triangle where the base is in the xy plane? The hypotenuse was formed by rotating from the z-axis. And then you need that base and the hypotenuse to form a triangle. They need to be like, one needs to be the shadow of the other, which is why I know they form a triangle. Okay, so I get my point right there. It's in like that quadrant. Okay, so now we can find the x and y coordinates of it. Okay, so it's fairly straightforward. You just start plugging stuff in. The x coordinate is rho sine phi cosine theta, which is equal to, my rho was 8 sine of pi over 6 cosine of pi over 3, which is 8 times the sine of 30 degrees is half, yes. And then what's the cosine of 60 degrees? Also half, right? Which, it's 8 divided by 4 is going to be 2. Okay, so this point right here has an x coordinate of 2. And then you find the y value, which is going to be rho sine phi sine theta. Your rho is 8. You have the sine of pi over 6. And now you have the sine of pi over 3, which is going to be 8 times a half, and the sine of 60 is going to be root 3 over 2. So you get 2 root 3. And this matches with my drawing so far. You can see that that point right there has positive x and positive y values. So we're like, hooray. So looking at the picture, I know I should also have positive z value. So let's calculate that. So z is equal to rho cosine phi, which is equal to 8 times the cosine of pi over 6. The cosine of 30 degrees is root 3 over 2, which is 4 root 3. And that makes sense. We got a positive z value. So that point that I made has coordinates 2, 2 root 3, 4 root 3. Hooray! Okay, making sense so far? Any questions on any of the calculations or the drawing of the thing so far? Let's convert from spherical to cylindrical. Luckily, we've done most of the work, and you can just sort of look at the picture. So remember, for cylindrical, you have r, theta, and z. Okay, so remember the z variable from cylindrical is the same as the z variable from rectangular. So we already know what z is. It's 4 root 3. Because it came from here. So once you find rectangular, you've got your z. What's also really nice, or not actually, my bad, but yeah, what's also really nice is what else do you also know? You know what z is, and you have one other thing. What's the other thing that you know? Yeah, exactly. Because theta matches up, so you know that theta is pi over 3. So you're like, yay! It just comes from the theta, right? Because they both are the angle of rotation from the x-axis in the xy plane. So you're like, oh shit, okay, this is not that bad so far. The only thing you need to figure out is r. Now, what might you think r is? Because I said, oh, what do you think it might be? It might be this. Oh, yeah, so you would think that it's 8, but it's not, and I'm going to point out why. Okay. What the hell? There we go. So 8 is your rho, which is the distance from your point to the origin, which is this white line right here. But r is a distance in the xy plane. R is this red line. So it's not 8 because rho is the distance from your point to the origin. R is the distance from the origin to the projection of that point into the xy plane. So you want to figure out what the length of this green thing is right here. And actually that's not that hard to do because we have like this triangle. The triangle with the rho, the r in the xy plane, and then the dash dash dash. So what you have is this triangle. Does it make sense? This triangle is this one right here. I'm like putting the lines. So let's like draw it nicely over here. So you have this right triangle, you're solving for r, the height was z, and the hypotenuse was rho. That comes from that triangle that I've drawn above. Okay, I'm gonna pause. Does it make sense how I labeled that, where I got r, z, and phi, rho from? Because if that doesn't make sense, then you're sort of stuck. Let me draw the r nicer. Okay, now you have some of this already, right? Z is equal to 4 root 3. Rho is equal to 8. You can just use the Pythagorean theorem to solve for this. We know that r squared plus z squared equals rho squared. So r squared plus 16 times 3. Shit, what's 16 times 3? 48. And 8 squared is 64. Crap, what do you get when you subtract those? 16? 64 minus 48, 16. I'm just gonna wait for affirmation. I don't feel confident in my mathematical abilities right now. Okay, good. So when you take the square root, you get 4. So here are your cylindrical coordinates. Whenever you do this, you can just steal the theta from spherical. You can steal the z from rectangular. The only thing you need to solve for is r, and you'll use the fact that r squared plus z squared is going to be equal to rho squared. Boom. That's how I like to do it. There's like other ways. I think this is the easiest. Okay, I think we're done.